similar, not there. So how would they change?
I don't know.
Maybe the functional group would, the position would change, or maybe the alkyl group would change. Yep. Or maybe we have different types of phenolic compounds. So why are these phenolic compounds so special or so poisonous? Anything that you know about phenolics? Do not know. So phenolics actually they are in the environment, and they are, what's the formula for phenol? Benzene with an OH, and some we might have CH3, yeah, and CH3 can be an auto meta para, so they are all different, and some we got a different alkyl group. So all these phenol, they are simple compounds, they are poisonous, they are quite poisonous in the environment. So sometimes we need to separate them to analyze. Maybe some are more toxic than others, correct? So that's the reason why we need to do separation. So Dr. Wong will go through all this in great details. All right. So for my part, is mainly we are going to look at biosensors. Okay, if you look at these two probes or these two sensors, so this is what? Thermometer, right? So what does thermometer measure? Temperature. What are parameter? Chemical or physical?
Physical.
Huh? It's a physical parameter. That's correct, yeah. So it's a physical sensor, correct? What about pH probe? pH electrode, so what does it measure?
Chemical sensor.
Huh?
Concentration of H plus.
Concentration H plus, that's correct. So H plus, is it physical thing or a chemical thing?
Chemical.
It's a chemical. So actually in this tray, we have got a sensor that detect what? A physical parameter, and also a sensor that detect H plus, which is, so we have one physical sensor and one chemical sensor. So this one I don't have any biosensor. So but this one, so what is this one, Ruben?
Glucose strips.
Glucose strips. So actually this strips is actually some leftover used on the glucose meter. So you understand the the government is talking a lot about the white rice, white sugar, white bread, all this. So this is actually for the detection of glucose. Okay, let's open it. You didn't open, right? It's an old one. Doesn't. Let me see. Okay. So if you look at this one, this is actually going to the meter. So how many this one we are going to have electrodes actually. These are all old stuff, doesn't matter. So this one is the connector. Actually, you know how many electrodes are there? Can you see? One is like a U, no. This is just the line. No, in fact is, how many? You think you can make a guess? You think you can? They are actually, I'm very scared of that coffee there. Like in the lab, you do not put things at the edges. Put at the back. Actually, if you look carefully, there are 3 electrodes. Yeah, I'm very particular. I think there are switches inside.
Yes.
I'll ask you to pay. There are actually 3 electrodes. Yeah. If you look, there are actually 3 electrodes. So this one is actually a glucose biosensor because there is a biological component. So it's a sensor, but at the front there's a biosensor. So literally I'm going to, So we are going to look at biosensors. So it has a biological component. So the biological component can be, what are things are from biological source? Enzyme, yes. What else? Microorganisms. Yeah, some of these microorganisms can be used to make electrodes. Maybe I have a slice of apple. Because apple has enzyme. And no bio teacher here, any bio teacher? Yeah, enzyme, and even banana, mushroom, liver. Liver is an organ that detox. So there's a catalyst that detox H2O2, detect H2O2. So the biological component plays an important role for the development of biosensors. So basically we'll spend quite a fair amount of part of the lecture on that topic. Alright. So you are going to, your assignment, you are going to use biosensor for the detection of all kinds of analytes. All kinds of analytes. Okay, one of you is going to do DNA biosensors, right? Is it correct? Okay, DNA is also biological. So where do you get DNA from? From cell, yeah, we extract from, could be from blood, from living. So it's biological as well, could be RNA as well. Alright, but DNA is easier to handle, RNA a bit more challenging. Alright, so we'll go to my part. This one Dr. Wong will cover. It can be quite intensive. Can you do a bit of reading before when you have time? Do a bit of those reading, yeah. Okay, we will look at different kind of biosensors. Actually, biosensors, they are very interesting class of devices for the detection or a range of analytes. Could be from environmental, from our body. So what are the problems we have? Glucose, what else? What are the parameters that we're interested in? Sodium, yes. Actually, to detect sodium, we do need a biosensor. We do need a biosensor because sodium, I can just use, how do you measure sodium? I can just use a sodium normal electrode. I don't need any biological component for the detection of sodium. So, more interesting organic molecules in our urine and blood.
You just said urine and blood.
But the compounds inside.
Protein.
Protein, yes. What else? Cholesterol. Yeah. Maybe urea. Yeah, things like that. Even the different types of cholesterol, the high density and the low density cholesterol, things like that. Yeah. Ketone, fatty acids. Yeah. Sodium and H+, we don't need a biosensor for those detection. It can just be detected by a particular simple chemical probe. Those compounds I mentioned, the more interesting organic compounds. So those typically we need a biological component for its detection. Is that clear? All right. We will look at how do we classify. There are so many kinds of biosensors. So do we classify according to the applications or so there are certain ways. So we are going to look at two methods of classifying biosensors. Two ways. There's no right or wrong. Depends on so different research they have their preference. But you just look at it, it's just different approaches. So we are going to look at catalytic. So of course is done by the enzyme. Or the other one is bioaffinity. Bioaffinity will be things like based on DNA binding or what is that? Antibody antigen, the last topic, remember? Immunobiosensors. Yep. So those is one type. Right. We will take note. Transducing. If you look at different compounds, yeah, they have different physical properties. Some probably they can undergo reduction, they can undergo redox reaction. That means it can be reduced or oxidized, correct? Yeah, it can be, that means they are electrochemically active. That means I can detect those compounds by electrochemical method, that's one way. And some compounds, they give out light, they absorb certain light, is that correct? So for those, we can detect by optical method. And what is the other? Thermal. So thermal is what? So for chemical reaction, or even reaction, so it's either exothermic or endothermic. Is that correct? So some of these thermal properties can be used to monitor chemical reactions as well. Yeah, very straightforward. What is meant by this term immobilization actually? Immobilization, what is meant by that term? To fix it, that's right. Because normally many of these biological components like what? Enzyme, DNA, or even when I mentioned, of course, if I have a slice of apple, it's very cheap. One apple I can make into 1,000 small thin slices. Yeah, but like microorganisms, because we have to purify them. Protein, they're expensive. Enzyme, they're very expensive. So that's the reason why I don't want to have it like a one-time use disposable. It's very costly. So we'll immobilize the enzyme, or maybe I should use a more generic term, the bioreceptor. The bioreceptor. So we can use it, the biosensor can be used for many times. Understand? Yeah, can be used many times. And we look at techniques. So that part, immobilization will involve a bit more those who like synthesis, a bit of synthetic chemistry approach. But for us, we don't go to too much. As long as they can be used, some of the simple methods. Very simple organic chemistry. And for immobilization, there are two kinds of immobilization. One is chemical method, need a bit of organic chemistry. The other one is just physical actually. Physical, literally, if I have this is my biosensor, I'll just press it. Because enzymes or some of biosensors, they can be absorbed. So absorbed, AD or EB?
D.
AD. Yeah. Okay, enzyme can be absorbed on sensor surface. AD, alright. So this is actually just a surface phenomenon. Yeah. So those are the simplest. Trends and issues, that's why we have got what? Who is doing lab on chip? Charlene, right? Yeah. Yeah. Because why is lab on chip so interesting? No idea. Why is that?
Can be carried around.
Can be carried around, yes. Put in my pocket, yeah. And what else?
What's the one where they put inside?
Yes. Yep. Because lab on chip, maybe I have a 50-cent coin, yeah. It's good, it can be used to detect 100 items from the environment. Yep. We want everything to go down to a small scale. So this one we ask Charlene to explain the trend to us. Yes. Because and very often, all this, we want the chemical reagent. Who have done? Farhan, you have done green chem, right? Why do we want to scale it down, right? Remember? You were in my class or not?
I got B minus.
B minus, why? What, Cairo get better, right? I don't know. Anyway.
We all did badly.
Huh?
We all did badly.
All did badly, yeah. So I hope this time you all don't do badly. Okay. Yeah. So we want to reduce the amount of reagents used for the analysis. Basically, if we use a small detection surface, so the amount of reagent used will be less. Yeah, we want things to go, and let's say the reaction will be completed in a shorter time as well. All right. I think that one we'll let Charlene explain. So some of the trend, I'll just explain a little bit in the introduction slide. Let me go on. Okay, so this one we have done. So if you look at glucose, cholesterol, HDL, blood, ketone, this is the fatty acids. Yep. So these are for different kinds of those. So Jason, if you see, sodium is not there. Probably even calcium, things like that is not there. So many other organic. We need the enzyme part. Okay. What is the typical method for those diabetic patients? What do they use? What is the body fluid for the detection of glucose? They prick their finger. So what is the medium? Blood, yes. Okay. We do not want to, let's say 1 test, we take 1 ml of blood. They have to monitor, I don't know, 3 times or 4 times. 1 ml is too much. So that's the reason why we have to go down to what? Smaller scale. If not, the patient will not die of diabetic, but die of not enough blood in the system. You understand? The logic of a macro analysis go down to micro or even nano eventually. Right? So this part. So eventually, actually, scientists, they would like to actually just put a probe here. So that one, I don't know how accurate, I don't follow too much. Put a probe on the body, see whether we can measure the glucose level accurately. So I'm sure scientists are working towards those type of group. It's better actually. That means it's not intrusive, so you can just measure. So of course this one, maybe the error will be bigger. You understand? So there's a lot of money in making of all these biosensors. I'm sure these glucose test strips, every day is like you have to take your breakfast every morning. So these strips are being sold, mass produced, so a lot. The market is really big. This is our bad lifestyle and not healthy. Okay, this one done. This one done already. We have to characterize. When you develop something, you have to characterize. What are the characteristics of a good biosensor? So this one a bit more general. Immobilization, transducing. So transducing, we might look at whether what is the property during the biological reaction. What is the property we would like to monitor? You understand? Could be light, could be electrical, could be change of the light intensity, things like that, or could be chemiluminescent, could be fluorescent. Yeah. Okay, for us, I will focus mainly on the electrochemical method. In fact, in the commercial market, the most successful biosensor that's in the market, can you make a guess which one is the most popular one? The analyte, of course, is glucose, you understand? Because it's really very prevalent. You can go Google WHO website, see how many people in the world are having this diabetic problem. So the most successful commercial biosensor that is being sold is actually glucose biosensor. and it's based on electrochemical. So just because electrochemical detection, we just need those electrical engineers to have a simple electronics, then can get the reading. Yeah, we don't detect light, and light probably is harder. Why is light very hard? Blood is it has already got color. You understand? So it's better to use electrical chemical signal to either oxidize or reduce the species. So blood, to do blood detection, detection in glucose in blood medium is challenging because of the color. Yeah, and of course we can separate the plasma and all the solid part, but that one we can't do this at home. Do you understand? Do you see the challenges? So the red blood cannot do optical so simply. So ideally it should go through a chip. They separate the sediment and then they measure the glucose in the plasma. Yeah, it's more tedious. That's why electrochemical is more direct. Yeah. So we'll spend more time on the The light one I'll just go through, introduce, and that's it. Yeah. So if you look at a very simple biosensor, how many parts are there? If you look, the contrast is not. You got the analyte. What is in the orange part? The bioreceptor. Yeah. And the transducer is the part that carry over that whatever happened at the biological part. So it carry to make it into a readable signal. Of course, processed by the engineers. So if you look at a biosensor, what are the people needed to develop a commercial biosensor? Of course, we need a chemist, right? Who else do we need? The engineers of course, basically are just these two groups of people. You understand? Yeah. To process the signal. Right. Let's move on. Okay. This one I think no need to go through. I change this a bit. I think I need to put this down. If not, everybody will just keep quiet, don't ask questions. And then I'm the bad guy, keep asking questions. So everybody must participate. You understand? But so basically I want to make sure everybody is active. No, I think that one, your slide initial one was not there. Yeah, just change this one a bit. Yep. Okay. Literature. Okay, when I look at literature, so what are sources that you all like to cite? You have done your previous assignment.
Wikipedia. Wikipedia.
Oh no. Ruben, this is your second semester, right? So what are references do you cite for your assignment? Journal articles. Jason?
Journal.
Really? All journal? But is it all open access?
No.
Can you access NTU journal articles?
No.
They are the open access one. You just search for the gold.
I know, open access, yes. But in your assignment, you can have a mixture of open access and some real journal, the closed one. Do you know how to get those? You have to go to NTU and get it. Do it physically. You come to class early, or Saturday you have to come back, then make sure you come back. You read through that, if something is interesting, you want to get them, then you come. You understand? I allow some open access, Wikipedia, yes, 1 or 2 sites, okay. But not everything is from there. But it looks really bad on it doesn't look so fantastic. Yeah, the impression is important. Get some real journal, a bit of open access is fine. Maybe half. Yep. This one, any question? And whatever thing you put on your slides for your presentation, make sure you understand, prepare well. So when people ask, you can handle most of the question. A lot of students, you all tend to put a lot of very sophisticated things, but when people ask, you cannot answer. Make sure you read whatever that you put on the slide. Yes, that will be good. Yep. Okay, we'll look at topics. History, never mind, this one can move on. Okay, look at electrochemical, I'll cover all the topics. So if you look at electrochemical properties, what are the parameters that we can measure actually for electrical thing? So when you do what are the things we can measure? What is that?
Current.
Current, yes.
Potential difference.
Voltage, what else?
Resistance.
Huh? Resistance, yeah. Actually, resistance is a good one. It's related to the conductance, actually. It's the opposite. Yeah, it's the opposite. It's all correct. Of course, another method is actually coulometry. We are measuring the charges. Yeah, that one not so useful in our biosensor development. Is that clear? And optical, the absorbent, fluorescent, they are all inside there. And thermal heat conduct. So piezoelectric, literally maybe we stress certain material. Yeah. So we stress. How do we stress the material? By stamping. Actually, we are stressing. We are actually putting stress on that particular site. So this one, the charge distribution on the material will change. So this one sometimes can distribute. We can generate electricity. All right. And sometimes some of these, when I say putting stress, even absorption of certain material is literally stressing. Some of these methods, they are very sensitive. When something is very sensitive, is that a good or a bad thing? Huh? Okay, what's a good thing?
Gives you accurate readings.
What is it?
Gives you accurate readings.
Not quite.
Unless it's...
Not say accurate. That means it can detect very low amount of the analyte. Yeah, it gives us very sensitive reading. Sensitive reading, yeah. Yeah, because when for certain illness, yeah, the biomarker is present at a very low level. So we want a very sensitive method, yeah, that can detect the changes. Okay, so that's the advantage when it's so sensitive. But what's the disadvantage?
False positive.
Correct, yes. False positive. Or even if I sneeze to the sample, I'll generate a signal. Yeah, it's possible. That's correct, yeah. False positive means I do have cancer, but then because of this false result, that then it's not good also. Correct? Yep. So whatever sensor you develop, make sure it doesn't give you false positive, it doesn't give you false negative as well. What is meant by false negative?
Cannot detect the level. Cannot
No.
detect.
If the method is not good enough, that could be one method, but sometimes they give you, actually you are supposed to have, but then due to the interference in the matrix, it say it has got nothing. It's not only the not sensitive, that one is just the limitation of the method, but then sometimes due to that detection, there is interference there. Is that, Jason, you understand what I'm trying to, like if you look at drain water and sea water, what is the difference in the matrix? That one has a lot of sodium chloride. The drain water doesn't have. So the presence of the sodium chloride might mask the actual signal of a particular analyte. Yeah, that can give you a false negative. Yep, can give you a false negative. Okay, let's move on. Techniques, because many of these bioreceptors, the living things like cells, tissues, actually tissues, probably if I say tissue, it can be a piece of mushroom, a slice of liver, can be a piece of banana. Actually, sometimes these tissues, they are not so expensive. Enzyme usually is expensive, DNA. Okay, microorganisms can be expensive because we have to buy them, they have to be have to be purified. So immobilization, how do you characterize, yeah? Right, application trends. So this one actually, most of these, we are going to cover in your presentation, is it correct? So everybody will talk about different applications, yeah? Different applications. So this one you will cover. Ruben, yours is screen printed, right? So maybe you can have one, no, but it's all environment. Then I can't, then you have to talk about just environment in different medium maybe, all right? DNA, maybe you can talk about disease, environment, something like that. Is that clear? Or even carbon nanotube, maybe in pharmaceutical, one example, another one, something else. Yeah? Alright, I hope you can approach. Okay, let's move on quickly. This one done. Okay, if you look at, okay, this table is really big, right? So I don't expect you to, there are lots, they divide in a very, detail, I just get it from a textbook. So we will, so this one we will cover in a greater detail. In fact, we spend a lot of time here. Absorbent, I will just do a bit on the absorbent when they do sol gel, biosensors. The rest we don't do actually. Okay, surface, SPR. Any of you doing SPR? Nobody? Okay, this is a very sensitive technique, but very expensive because the sensor requires a gold film. I just have one slide later on this SPR. But the technique is very sensitive. Whenever there's a bit of binding, you change the surface properties. The angle changes, then it can detect, maybe good for detection of certain disease. Very thermal. I might just cover a little bit. This one I will not even cover. Some of it won't cover. So basically, this table is very big. No need to worry about the content. Don't worry too much about the content. As we go, I will go the electrochemical part. Okay, let's move on. Others, where's the next one? This one, okay. Where's the biosensor? Let's move on now. Okay, basically, if I have a glucose biosensor, what are different types of carbon-6 sugars? So glucose is what, C6, right? What other sugar there's 6 as well? Maybe fructose, I think has got C6 as well. So what about the sugar cane sugar? What is that one? Sucrose, yeah, that's correct. I think that one is C12 actually. That one is C12. But anyway, we got glucose, we got fructose, we got what? Sucrose, right? And we got mannose, we got so many sugars. So basically, let's say if this is a glucose biosensor, it's just selective for the detection of what? Glucose and not other sugars. Do you understand? So the selectivity of biology, that means is determined by the selectivity. The selectivity of a biosensor, is actually determined by the bioreceptor. Okay, let's say example. You see, I will just always refer to glucose, and so let's say if the glucose biosensor, okay, the bioreceptor is, some books will use it as GOX, glucose oxidase, or some will put it like little god, glucose oxidase. But literally, the selectivity is due to the presence of what? That enzyme, very selective enzyme for the detection of glucose, is glucose oxidase. So let's say this enzyme will not act on the other types of sugars. Is that clear? Yeah. Probably just as another example. Okay, in fact, this example, if you notice, I'm going to use. So, what is this? What did I write? Urea. So, what is urea? Anything you know about urea? What is that? Ammonia. Yes, it forms ammonia. So urea is one of the indicators for our kidney function, I'm sure, and probably a lot of decaying process in the environment, in the water body. You release urea as well. Decaying or organic. What is that?
Deamination of amino acid.
Yeah, you have this. So the enzyme that will act on this is the hydrolysis. Is actually urease actually. So if you notice in the class, I'm going to use this group as the subject of introducing a lot of teaching about, because they give very interesting products, and the products of detection will allow us to different type of detection. So if you notice just now, we have got the analyte, then we've got the BR is a bioreceptor, and of course we need a what? Transducer. Okay. So the word transducer is a Latin word. It means what? To carry over. Then it detects the changes of the interaction of the analyte plus bioreceptor. Yeah. So you process the signal, carry, and then they subsequently processed by the signal. All right. The bioreceptor has to be what? Has to be immobilized. Typically, let's say if I have glucose, I throw the enzyme in the solution. Does that work? Would there be any reaction? Glucose inside, and I have a sample of urine or blood. I throw in my enzyme. Would there be any catalytic reaction? What do you think? It's all mixed. Will there be Basically, the analyte and the bioreceptor has to mix. They have to mix. But in this case, the actual mixing is just, I'm going to throw too much enzyme inside. So when I have a biosensor, everything is what? In this is my electrode or whatever, my probe. Then I have got a little bit of enzyme. This enzyme is stationed or immobilized on the surface. So this probe, glucose probe, can be used to measure one sample, second sample, third sample. And of course, in between these, we have to do washing. If not, there will be carryover effect, correct? Yep. So of course, the mixing, it works, we can detect, but it will be too costly. You understand? It will be too costly. All right, the target analyte. Let's move on to the next one. Okay. If you look, there are a lot of definitions of the biosensors there. So basically, they will use the word integrated. You can, okay, some of these, a bit of this, you can use it in your assignment if you think it's appropriate. Yeah. So some of the characteristics. It's a device. Biosensor is a device, and then normally the signal is proportional to the concentration of the analyte. If you summarize the slide, and then the device must have a biological agent. Actually, biological agent. Of course, the more specific name is what is the more specific name? Wait. The device must have a biological component. Bioreceptor. It's a receptor, but of biological origin. Yeah, the biological agent, or the term is actually bioreceptor. This one can be enzyme, can be cell, can be tissue, so on and so forth. Yeah, can be DNA, can be antibody, Yeah, all right. Yeah, let me see. What is important? These are some of the analytical characteristics. What is this one? It has to be reproducible. What does that mean? That means if this sensor measure one sample today, give me a signal of 10 units. Tomorrow, give me 10 units as well. It has to be reproducible. And then in the afternoon, give me half the response. Half the response, what does that mean? It could mean the environment is very clean, no more pollutant. And usually we want the response time. Why is response time important? If I have this probe in the hospital or in the analytical chemistry lab, in a commercial lab, they will have lots of samples. Maybe Farhan can testify. Pipette until what? You have lots of samples to do, right? So the analysis time has to be what?
Short.
Has to be short, yeah. Because, yeah. If you notice, there are some examples I give, very extreme one. Certain measurement, it takes like 1 hour, one measurement. So actually this type of biosensor is what? It's bad. It's not good. That means one day I only do 8 measurements, then can go home already. But certain measurement is tedious, yeah. So actually, come back to Charlene's title again, is what? We want things to be smaller, so reaction can be completed, turnover time is faster. Yeah. So some of these you can read. Usually, there are 2 classes of, one is what? Biocatalytic. The other one is bioaffinity. We are coming to this slide again. The class 2 types, bioaffinity. Okay, catalytic, the very typical one is always enzyme. It's always in our mind. So actually, enzyme electrodes are the most common one. Yeah. So based on enzyme, this one maybe I'll use the word microorganism. Microorganism could mean what? Those living cells. Yeah. Cell for the environment. Yeah. So bioaffinity could mean antibody, antigen, yeah, AG. This is not silver, antibody, antigen. Take note, usually when antibody and antigen bind, what happens? What happens to the binding? Any idea? The binding is very strong. So this is not reversible actually. Usually for this type of biosensor, we can reuse actually. Usually, we can reuse them. Yeah, because it's reversible. Yeah, we can activate. Take note, usually when antibody and antigen bind already, we cannot split them because the binding constant is very high. Yeah, the binding is extremely high. But the other kind will be what? DNA. What are the bases in DNA? Got what? Adenine, AC, cytosine. What is that? AC, thymine, is it? Guanine. So they pair up. So this one is once they pair up, it's very hard to open them as well. Alright. So this side is irreversible actually. Alright. The rest you can read on your own. Yep. Yeah. Enzymes, they are reversible actually. The microorganisms, yeah. Once you wash, they can still function. Because once there's a substrate for them to catalyze, they will catalyze. Yeah. All right. Okay. If you look at these slides, this slide, if you look, the analytes. So assuming the triangle is glucose, all right. Assuming the triangle is the glucose, the rest are different kinds of sugars. And on the surface, so for enzyme, the normal mechanism is what? Lock and key, right? The mechanism. So assuming these are the glucose oxidase on the surface, yeah. Of course, this part, the light one, we can tell you put down as what? Molecular recognize. Put down big bracket as bioreceptor. Okay, it can be enzyme, antibody, microorganism, cells. Maybe you can add one more. You can put down DNA. DNA, can put down maybe a slice of tissue. Yeah, can be a slice of tissue. We can be rich in a particular enzyme. Yep. So I still put it as tissue. Yep, because that particular part has certain enzyme. Alright. Yeah. The signal transducers, we will have the properties. So if you have got heat, I can use thermistor, heat change, that is an endothermic reaction. I can use thermistor or I can use a thermometer. Okay. If you use this normal thermometer, right? So this one is not a biosensor yet. How do I make this in a biosensor? I need to coat a layer of bioreceptor. This is a physical sensor at the moment. Correct, just a physical sensor. But if I coat a layer of cells, and this cell catalyze a reaction or it causes a reaction to happen, assuming it produces heat, what will happen to the temperature? You can measure. When there are lots of analyte, the temperature change will be greater. Is it correct? Yeah. So from this simple thermometer, I make it into a what? Biosensor. So what do I have to put here? A bioreceptor, a suitable bioreceptor. All right. Next, pH change. Okay, what is this one? This is just a simple one. pH electrode. Technically, it measures H+ concentration of pH. Correct? Yep. So in this case, if I put it in different amount of sugars, what will happen? Because sugar is not acidic, it doesn't have any amount. So one of the reaction of glucose is, so if I put this in different amount of sugar samples, nothing will change. The pH stays the same. So what are the reaction for glucose? Alright, glucose oxidase. So obviously we need oxygen. Okay, what enzyme do we need here?
Just say the glucose oxidase, right?
Yes. Just test on you, glucose. That's correct. Then glucose is an oxidase. Of course, we need O2. Correct? We need O2. And this one, the product is actually Ga, gluconic acid plus what else? H2O2. Yeah, okay. Alright. Take note. So this is a simple pH electrode. If I put it in different amounts of pair electrode, put it in 1 millimolar, 10 millimolar, 100 millimolar of glucose, the pH will stay the same. Do you understand? But if I, let's say, what is the detection surface for glucose, for a pH electrode? Is it solid? What are solid? Any idea? Oh my god, this is wrong. This actually, this is not glucose. This is not a pH electrode. This is actually something else. The glass electrode. Have you seen the pH electrode? Ruben, how does it look like?
It's like a ball.
Like a ball. That's correct. Like a ball. This one, if you look, what is this? It's flat. It's not a glass ball. Just physically, I fool your technicians. So for a glass pH electrode, it should end up like this. Maybe some of you can Google. It's like this. This glass is very thin, actually, very thin. That one, in fact, is flat. Okay, assuming that one is I put in 1 millimolar, 10, 100 millimolar glucose. pH stays the same. So that one, this one is not a glucose biosensor. So what should I do?
Cold.
I have to coat, yes, at the moment I use the word coat, but actually we cannot coat the enzyme because enzyme is soluble in water. I have to use a membrane to trap it. Yep. Use that. I have to put a layer of enzyme. What enzyme must I use? GOX, yeah. But I do not want the enzyme to go into the solution. It has to be you understand the term dialysis membrane? So what does dialysis membrane contain on the surface? What word? Pores, cannot use holes, okay? Pores, that's right. Dialysis membrane has a lot of pores. Enzymes are very big, so if I trap the enzyme like a net, enzyme will not come out, correct? But the analyte, what is the analyte? Glucose is very small, relatively, it can interact. So if there's a lot of glucose, what will happen to the gluconic acid form? If the amount of glucose is very high, I'm diabetic, it's diabetic. So what will happen to because this is 1 mole produce 1 mole. Then of course this is high, GA will also go up, is it correct? GA will also go up. So what will happen to the pH? What will happen?
Go down.
Gluconic acid goes up,
Reduce.
pH will drop, that's right, yep. So if let's say for a person with very diabetic, sugar level very high, what will happen? Of course the pH will be lower. Provided that particular pH electrode has got a layer of GOX. Can you see the concept? So actually I give you the gist, everything is very simple. For all these physical sensors, we can make them into what? Biosensors, is it correct? Provided we introduce the correct one. Correct bioreceptor, that's right. Correct enzyme, correct bacteria, or correct DNA. Is that correct? Alright. Electrode, light, photon, mass, okay. This is piezoelectric, then we get the electric signal, done by electronic. Okay, that one is done. Let's look at a bit of history. I think this one I won't spend so much time. A bit of the historical development. If you notice, what is the okay? If you look at 1, 2, 3, I keep put the word pH rate. Is it correct? If you notice, pH, the word is always is about more than 100 years ago. People are always very interested in the concept of this pH. Even 100 years ago, 1909, concept of pH, rates of enzyme hydrolysis. Because if let's say pH is very extreme, what will happen to the enzyme? Enzyme will die, denatured, that's correct. Yep. So the pH where the enzyme can function well is in a very narrow range. Is that correct? And the pH of live red blood cell, so even in the old time, people are interested to check the health. What is this one? Mammalian tissues, solid metal. Basically, it's actually, for a long time, we are interested in the pH measurement for medical or even for what? For the fruit industry, actually. For the fruit industry. And so he thought it's all started with pH. Then this is also electrochemical. All these are all, so the pH measurement is literally electrochemical. Of course, we also can use, what other method can we use to measure pH of solution in the school? You can only tell whether it's litmus red or litmus what? What is that one?
Blue.
Blue. You can only tell alkaline or acidic.
Universal indicator.
Is that? Can you see a good color change?
Not very good.
Very distinct near
Al-
7 pH.
At pH 7 not so good. At the acidic, at the extreme.
At pH 7, at pH 1 and pH 14, very good. But
Yeah.
anywhere in between is very good.
Yeah, you just can't tell. So actually we need a pH electrode to measure. Then what about the health of our stomach? Our stomach, right? What's the pH in our stomach? About 1, yeah. So let's say so scientists we want to see whether our stomach has a problem or not. Put a micro electrode inside, micro pH electrode to check the health of our stomach. All right. This one I might just go through. So the measurements of this one I will just the measurement of H plus in the solution is always of interest among people from different traditions, yeah, different areas, medical industry, what else? In the orchard, the food industry as well. For years and years, after you see a very bulky pH meter, the historical. So this one, what can you describe what you are looking at? You know what you are looking at?
Hydrogen electrode.
Hydrogen electrode, that's right. So hydrogen electrode, what is the chemical reaction? So our reaction is always written as reduction, is it correct? So we're going to H plus E give us what? Half H2. Alright? Yeah. So this hydrogen is literally we are more interested in the H plus in the solution. Alright? Yeah. Let's move on. H plus, okay. Basically it's just concept of H plus. Okay, this one, so this, who is this person? Batman actually. But he make a lot of things. He's a Caltech professor. He's actually amazing, I would say. For me, I don't know anything about it. I can't make any circuits. So he can make both things. So what did he construct for his friend? Because his friend has a problem that he want him to solve. What did he want to solve? It's actually to measure the citrus, to measure how sour the oranges, the lemons are. Yeah. So at that time, he didn't even call this as a pH meter. He just want to indicate. So the old name for that time is known as what? Acidic meter. Acidic meter. So this was invented like more than 100 years ago. Yep. So he knows the chemistry, and you see how bulky the item is. It's in the box. Yeah. Because the electronic, all this is very bulky. So that was the first pH meter that was ever made, like I think less than 100 years ago. You understand? But at the moment, our pH electrode can be as fine as even smaller than a matchstick. You understand? It's from big to become micro. Alright? Let's move on. Okay. We look at the more electrochemistry, a bit of electro. So what is DME? What is DME? Dropping mercury electrode. Yeah. So this slide is the reason why this slide appears. What are the gases in our atmosphere? The major ones.
Nitrogen.
What is that?
Nitrogen.
Good. Of course, oxygen. What is the next one?
Carbon dioxide.
Carbon dioxide, in fact, is not so big. Maybe just this few, you know. And you got all the trace, you got all the others. Okay. If you have got this and this, yeah. Carbon dioxide probably at the moment I'm just going to discuss these two. Carbon dioxide, of course, it affects the pH of the water body, pH of the blood, pH in the stream, in the ocean, so on and so forth. Okay, this one is about 80% or
78.
78. Okay, this is what?
21.
21% volume. Okay, if you look at this thing, so what does this slide tell you? What are we measuring? What is the key component we are so which one is appears? Oxygen or nitrogen? Oxygen. Yeah, if you look at this slide. So basically, let's say if a solution, of course, water must contain oxygen, correct? Without oxygen, living organism cannot survive, right? So the measurements of oxygen is so just now is a measurement of what is the other species earlier on is H plus, correct? Yeah, slide shows the various applications of H plus. So this slide shows the measurement for O2. Okay, O2 is also important because of what? It will affect fermentation, the blood cells, so on and so forth. So it has industrial as well as what? Clinical consequence. Is that clear? Right. This slide literally, it shows that this term we use it again and again. Oxygen is electrochemically active. What does that mean? That means oxygen, if you look at this reaction here, this is oxidation or reduction reaction. What is that? Reduction. Basically, oxygen undergo two-step reduction. So the first step reduction, it produces what? Hydrogen peroxide. Are you following? It produces hydrogen peroxide. And the hydrogen peroxide undergoes another step of reduction. And what is the end product? Water. Yeah. So that's the reason why we say oxygen is electrochemically active. What about nitrogen? If let's say I got this beaker of solution, I purge the solution with what? Nitrogen. What happened to the oxygen now? Oxygen will be displaced, actually, will be chased out by the nitrogen. So now the solution just contains what? Dissolved nitrogen. But when we do purge the solution, this is before purging. First reduction process, then got the second process. So this curve here is actually will purge the solution with what? Nitrogen. Are you following? Purge the solution with nitrogen, what happened to the line now? No more signal. Yeah. So in contrast, so what can you mention about the properties of nitrogen? It's not
electrochemically active.
Electrochemically not active now. So nitrogen is electrochemically not active. That's correct. Yeah. So you see, what is nitrogen is an inert gas. It does oxygen promote oxidation. If we store something in nitrogen, preserve a lot of biological sample in liquid nitrogen, the integrity of the sample will be preserved. Is it correct? Yeah. So oxygen is chemically reactive. Chemically active is also electrochemically active. Nitrogen is electrochemically non-active. Yeah. All right. So this one is flat. Yeah. Yeah. Okay. Let's go to the next slide. So during the old days, yeah. So oxygen was measured using what? DME, dropping mercury electrode. So eventually we are going to, if you look at, okay, can I bring to that reaction again? Can you look at glucose plus oxygen, GOX, given those reactions? So what can you comment? Can you say something about the reaction? If there is a lot of glucose in the sample, so during that catalytic reaction, it will consume what? A lot of oxygen as well. Correct? Yep. It will consume a lot of oxygen as well. So the level of oxygen will actually drop if there's a lot of glucose. If you want to do analysis, I mean when we are trying to do analysis, yeah. Yeah. Let's go to the next slide. Yeah. Maybe this slide again. So this is still oxygen. So during this time, in fact, if you look at this, can you look at the year? It's very what? It's even before the 1900, correct? So people were interested to measure oxygen as well. Yeah, interested. But the problem, they were using too large. So eventually I'm going to introduce a more very important oxygen electrode invented by the person Clark, by the Clark scientist. So this one is also no good. So actually those introduction slides, it will not really come out in the exam, just for the development of concept. Probably this slide will be the important one. Can you put a star here? This slide will be crucial. Right. If you look at these slides, can you look for the electrodes first? How many electrodes are there? 3 or 2?
3.
Why 3?
Because got reference electrode.
Okay. In fact, there are only 2 electrodes. The working electrode is platinum. Put down WE. Platinum electrode as a working electrode, alright? And then there's only one reference. Please do not mistake this one as 2 electrodes. It's actually.
And then what's the black line?
What is that?
What's the black line in between?
What is the black line? The body. I only see one.
The platinum electrode, the white portion, right? There's a single black line right in the middle.
That's a platinum. Okay, that's point.
Oh.
Okay, sorry. Okay, this is a working electrode. Can you put down working electrode here? This is a one line. The other electrode, the reference is what is the color of silver wire?
Silver.
Look metallic, correct? Yeah, that's right. It look metallic like a silver, like platinum, correct? But take note, this one is not pure silver. This is a silver wire coated with AgCl. Okay. Okay, teacher Jason, what is the color of AgCl?
White.
White or creamy, right? Is it correct? Or in school you
We prefer white.
use okay, I follow you. So this one silver chloride, is it soluble? Insoluble. So can you imagine the look of this wire? Can you describe the physical appearance of this wire? Is it shiny? It's not shiny. The surface has been coated with what? Silver chloride. Not shiny anymore. So Farhan, just now you mentioned 3 electrode. Is it because of you see Ag and also AgCl?
Yeah.
Okay. Take note, Ag/AgCl is one electrode only. Okay? Is that clear?
I think it's this line here that makes us think that they are 2 separate electrodes.
Oh, no. In fact, this is a platinum wire. When you say wire, how does it look like? If you look from the bottom, it's a disc. If you look at the plane. Yeah. Yeah. In fact, that one is just like a teflon or what. If you look at, this is the platinum wire. This is the working electrode in contact with solution. This structure, let me try to figure out. Electrolyte. Oh, I think the platinum electrode is actually like that. The white casing, the white part, right, is like a, what is that? Like a plastic casing that hold the wire. Yeah, like you have like electrical wire. There's a thick plastic casing. Yeah, that hold. If not, the wire is too fragile. You bend or whatever. Are you following? So the electrolyte is KCl. Can you just write down? This one, the book didn't mention any Cl because we need the KCl here. It can be KCl, can be NaCl, but usually we tend to use KCl. Are you following? Yeah, we tend to use KCl. So the reduction happened at the platinum electrode. What is the platinum electrode? It's the working electrode and it's cathode. At the cathode, if you want, you can put down PT here, PT electrode. So this reaction, what do we observe here? Reduction, reduction reaction. So what happened at the anode? Of course, at the anode, we need to have what? One side gain electron, the other side we what? Give electron. That's right. So if you add up the 2 equations, if you add up the 2 equations, what do we get? If you add up these 2, do we get this? Do we get this? Can you check whether the thing empty balance is overall? Add up the anode and the cathode. Do you get that equation? The final one? Is it? Can you think or no? Yeah, you get that one. Okay. If you notice, actually, this one, okay? If I omit all these, if I omit this, and omit this, do I get the same? In fact, the overall reaction is actually, one more thing. Can you add up these two, see what you get? Can you add up these two? These two equations, I get it from the earlier oxygen reaction, from the previous slides. Can you add them up? If you add up, I think we can eliminate the H2O2, is it correct? Yes? Yeah, eliminate the H2O2. I'm going to get O2 plus 4H plus 4E, right? And get 2H2O2. So, probably sometimes the oxygen reaction, we don't have to write we can ignore the AgCl. We can ignore this one. We can just give me this reaction. You can give this reaction directly. Are you following? Okay, let's look at the structure of the, why is this electrode known as Clark oxygen electrode? Why is this electrode known as Clark oxygen electrode? Of course, it's invented by the scientist. What is the name of the scientist? Clark. If you notice, there's one, can you see a gas permeable membrane? Can you see? Do you see there's a membrane there? Okay, this membrane is Teflon based. You have a lot of pores. It's porous Teflon membrane, so that oxygen from the external solution can diffuse through the membrane and undergo reduction at the which electrode? Which electrode? Farhan? Reduction at which electrode? Platinum or AgCl? Platinum, that's correct, yeah. That's a working electrode. Well, take note, it's a gas permeable membrane. If the membrane is very porous. When I say porous, this is relative, okay? For our naked eye, we cannot see the pores. Yeah, but of course the manufacturer, they can tell you what is the pore size, how many pores are there. If we stir the solution very fast. Let's say if this is an electrode, this is a beaker, we stir very fast. That means the diffusion of the oxygen is faster, correct? The faster, then the electrode response is faster as well. Yeah, the electrode response is faster. More stirring is required. So if we leave the electrode just stagnant in the beaker, what will happen to the response? Response is slower because we don't bring fresh oxygen to the membrane surface. Yeah. So normally when we do this kind of measurement, the solution is always being stirred, but at a constant speed. When I say constant speed means what? From sample 1, sample 2, all have to be same speed. Because if you stir faster, you're going to get higher current. Are you following? Because the response is faster. More oxygen is going through. Yep, those are the conditions you have to take note of. Yep, less stirring. Yep. Okay, let's go to the next one. What is the next? This one. Okay, this one I'll just have one thing. Just now is everything it was electrochemical, correct? Reduction of oxygen, detection of H plus. H plus is a bit special. That is not, we are not measuring the current, you understand? We are measuring the what? The charge potential or what? For this type of electrode, what are we measuring? What is the signal we are measuring? For this, for pH electrode, what do we measure? Is it current, potential, or what? Take note, for pH electrode, we are measuring the potential. But potential is converted to become pH. Take note, for this type of electrode, it's actually potentiometric. There's a relationship between pH and... Can revise a bit of your chemistry?
I forgot.
Take note, pH electrode is a potentiometric sensor.
I remember the one that I used back in NUS was a conductance measurement. They told us they're conductance measurement.
They don't say it's potentiometric for pH electrode. You go and see you go and refer to Scoot and Webb. It's always classified under, we are measuring the Nernst equation. Yeah, the Nernst equation. Yeah. Conductance, we are really measuring the resistance and we transform it into conductance. Alright? Okay, this is optical. This scientist is also very unusual. He's actually a scientist, he's a chemist, he's an engineer. He's also worked in the medical school. He did a lot of all this work, invented a lot of methods actually. In fact, some of his invention until today is still being used and of course being further developed. You understand? So the earliest is, and they make a lot of money for what's their workhorse actually. They make a lot of money for the company. They are spectrometers. So spectrometer, I'm sure you have used the UV measurements, right? So this one is a lab item that's present everywhere actually. Yeah. So this is optical method, and okay. If you look at a simple molecule of oxygen, does it have any optical properties? Does it have any? Never heard, is it? Of course, oxygen no optical properties. We cannot use optical measure for the measurement, but it has electrical properties. That's why we do electrochemical. Are you following? Sorry, yeah. Take note. You have to select. But you know what I'm trying to say. Oxygen doesn't have optical properties.
Okay, got it.
Got it? But it's electrochemically what? Active. Yeah. So you have to select the appropriate transducer for the detection. Yeah. So this thing doesn't produce color. You cannot do color detection. Yeah. All right. I think what's the next slide? This one. I think we can have a break. Then we'll go to the. Take note now. Clark oxygen electrode. What is the name of the membrane present? Clark oxygen electrode.
Gas permeable membrane made of Teflon.
Teflon is hydrophobic. Yeah. So after this slide, really, I'm going to skip. But if you look at this one is very complicated. You have to squint your eyes a bit. How many membranes are there? Then we can go for breakfast. Is your slide big enough? How many membranes are there? Enzyme layer. There are actually 2 membranes. Can you color code a bit? Oxygen permeable, put it at Teflon. The other one is an enzyme layer. What is that? You can go for a break and then come back.
Are we finishing the entire loan today?
Tonight, no, I don't think so. Why? Cannot. There are 2 layers. This is hydro. This one also got holes. Got pore, maybe not holes. Dialysis membrane. Simply we just put it as dialysis membrane. Okay. Can you think about it? There are 2 membranes. So from oxygen electrode, what do we make it into what? So oxygen electrode, what does it measure, Ruben? Oxygen. That's correct. Any biological component? No. But now we want to make the oxygen electrode into a biosensor. So we have to introduce the bioreceptor. You understand? Correct? Okay, what is the bioreceptor we use here? GOX, no? You can see GOX, right? Do you see GOX? Okay. So GOX, I represent as the crosses. Are you correct? GOX. So this membrane, there are 2 membranes here. The first membrane, the oxygen one, you're very clear. So I keep stressing the Teflon, hydrophobic. The other one is for oxygen gas to diffuse through. So the most outermost membrane is actually what? Dialysis membrane, which is very what? Is hydrophilic. What is the analyte of our interest in this particular configuration? No. I put put bioreceptor, no more oxygen.
Glucose.
Glucose, that's correct, yes. So glucose has to diffuse through this hydrophilic. Glucose is hydrophilic. So it will interact with the crosses, the GOX. Are you following? Yeah. When interact, during the interaction, it will what? It will consume you react, we need oxygen. Are you following? If the solution has a lot of glucose, that means it will consume a lot of oxygen in the reaction. That means the amount of dissolved oxygen in the solution will drop. And then the signal detected by the plug oxygen electrode will also what? Drop. Is it correct? Yeah. So let's say if I got sample 1, sample 2, if this is okay, if I got sample 1, sample 2, patient 1, patient 2, this is one, it has got 1 millimolar, this one has got 5 millimolar. Okay, if I'm going to, based on this configuration, so which, so take note, we are measuring the dissolved oxygen. Which sample will give us more higher signal? So it's a bit confusing, huh?
Higher oxygen.
Higher signal, I'm using plug oxygen electrode.
Patient 1.
What is that? Sample 1 will give us, because it consumes less oxygen. Yep. Are you following? Yeah, it consumes, yeah, that one will give. So take note, these equations, exam sure I'll ask, very simple, glucose plus. This one, I'm not interested for you to write the C6H12O6, those formulas. Just write word equation. What equation will you do? Plus oxygen DOX, gluconic acid. Even I don't even know how to write the formula of gluconic acid. Plus H2O2. Yeah. Take note, oxygen is electrochemically active, but optically non-active. Gluconic acid, we can alter the pH, is it correct? Yeah, it's an acid. Then H2O2. You think how is the best way to detect H2O2? You can refer back to the earlier slide. Do you think how can we detect H2O2?
Catalyst.
Don't make it so complicated. If you look at H2O2 can undergo what? You remember the 2 steps? Reduction, that's right. Take note, H2O2 is also electrochemically active. So actually, it's an interesting example. Yeah. So H2O2 is also good. It can undergo reduction. Take note, H2O2 do not underestimate. Actually, it can also undergo oxidation as well. Yeah, you can. So actually, there are different ways for this detection. You understand? Different ways for the detection. So take note. So is this a sensor or a biosensor now, class?
Biosensor.
It's a biosensor because it has what? The enzyme, the bioreceptor. Take note, this one when it was first invented, first described, so everybody was so excited. It was the first biosensor ever reported. Yeah, this is the birth with the start of the biosensors era actually. Yeah. Take note, this is a very bulky electrode. We cannot use it to measure blood because we need a lot of blood samples. This is one of the concept is there. Are you following? The concept is there to develop a biosensor, but it is not a very practical biosensor. Yeah, cannot use it to detect glucose in our blood because it's just too big. If you look at the strip just now, if you look at this one, it's very small. I can just put 1 drop of blood. That will be sufficient. That one I think easily we need 5 ml. Yes. But this is a very interesting concept that was first described. This one, okay. We are going to classify biosensors. Yeah. So maybe one way we can, based on bioreceptor, okay, I'll say glucose oxidase, glucose biosensor based on GOX. That's one way. Based on the bioreceptor. Are you following? That's one way. Or I can also say could be based on pH, urea pH biosensor. Correct? Can I describe? Do you think what happened to the urea reaction? I'm just giving you some example. Urea, yeah. What is the enzyme needed? Urease, that's right. It's actually hydrolysis, I think. Hydrolysis of urea, catalyzed by urease. We are going to get two gases, CO2 plus H2O. No, not H2O, ammonia. Sorry. Yep. Everyone? Yep. So urea, hydrolysis of urea in the presence of urease, the pH will change actually. The pH will change for that reaction. So you might say, will they neutralize? But it also depends on the Ka and the Kb of the system. In fact, it's about the Ka and the Kb of the system. Alright, so just like I said, glucose oxidase, glucose biosensor are based on the enzyme, the bioreceptor. So this one, you think, can you, so I give you a clue, the pH of the biosensor of the solution will change. You think, can you give me a creative way to name that biosensor? There's no right or wrong. You can say anything you wish. Just design one for me. Jason, design one. In fact, just like I did Arthur's answer. The pH will change.
Real pH.
Biosensor is fine. Or electrode. Some certain literature they use the word electrode. It's also okay. Yeah. I can say urea pH biosensor or urea pH electrode is fine. You understand? Okay. So okay, let's say if this one has got color, assuming this is not true. Assuming that one has got a color, it produces a color change. So Farhan, can you name me in another way? I'm detecting urea.
Then use
What is that?
Colorimeter or UV spec.
No, I want you to give me the name of that biosensor. Urea something.
Urea UV wisp.
No, no need to use UV wisp. You just say urea optical biosensor.
Oh.
You got the idea how to manipulate some of the possibilities. Maybe I give you a chemical reaction in the exam or whatever, hypothetical one. Yeah. I say give me two ways of naming the biosensor. Then you must argue your point. Fun, you see how I argue out? You don't use UV wisp there. You just say urea optical biosensor. That's the name of that sensor. Have you all got it? But of course, earlier on I said actually that one doesn't produce color, just for the sake of discussion. Yeah. Of course, pH I've given you pH. Yeah. So usually the word, you can either just put electrode or just put biosensor. The safest, I think, just put biosensor is the safest. You won't go wrong anyway. Yeah. So if you notice, we either use a transducing way to name it or use the what? The name of the enzyme. Yeah. Or maybe there are certain ways we say what? DNA biosensor for let's say X detection. Yeah, for X detection. So in this case, what is the method I use to name the biosensor? It's based on transducer or based on bioreceptor. Do you see any method?
Bioreceptor.
That's correct, yes. The keyword is this one, that's right. Yep. This is the so this naming, so I put down the naming of the biosensor can be based on bioreceptor or based on transducer. So from the word optical and pH, just now was based on which method? It's based on this one. Based on that one. But sometimes I say glucose oxidase or urease or glucose oxidase. That one is based on which one? Based on one. Yeah. Okay. This method, in fact, is a bit, I would say a bit more like Rojak actually. You can combine any method you like. Let's look at a more advanced kind of classification, a bit more atas, a bit more science. This one, and in fact, this one, anything goes actually, depends on what you like. It's, the definition is very loose actually. Yep. See how it sounds in your ear or see what the scientists are doing in the journals. Okay, this is what I said method A. Can we go to a more, slightly higher one? Okay, classification of biosensor method B. Can we look at this one? This one I sort of cover with you a little bit just now. More advanced classification. Okay. For us, we are looking at things that biotics. So biotic means what? Biological, right? So this is actually based on what our method is molecular recognition components. But actually we are not going to look at that part, abiotics. Abiotic, that means the part that recognize the analyte is based on non-biological one. So this part, what is that? Strike off. But I just put it as a concept so you sort of get the feel. We are if I just do this one, it's a bit unfair. This one is a bit open up a bit. Okay, have you seen, maybe just introduce very quick. Have you seen what is crown? What is, you know, understand what is ether, right? Lots of what? O, right? So what is crown ether?
Forms a ring.
What is that?
Forms a ring.
Forms a ring, that's correct, forms a ring. And then the ring can be very big, can be very small, right? If there are less components, it will be smaller one. So this crown ether, they are interesting, they can interact with a lot of metals. So let's say if you got lithium, sodium, potassium. For a crown ether to interact well with the potassium, of course the ring has to be what? Bigger compared to the lithium ion. Yeah. So this is abiotic. Okay, let's forget about that one. Let's come to this one. Yeah, it's based on molecular interaction. So actually biocatalytic we have done quite a few. We have done enzyme, very common. Tissues, why is tissues under this typically? Why is tissue under this? Because
Contains a lot more.
certain specific enzyme. Probably like banana, we have what? Polyoxidase. That's why it give you the browning. A mushroom, where certain or catalase will be present in the liver of a chicken. You can use that. Or even potato, things like that. Yeah, this is biocatalytic. Reaction is reversible. We can activate the enzyme. Okay, this is bioaffinity based on DNA RNA. Are you following? So this one, once the DNA binds, very difficult to open them up. So can you see that? So now I'm going to discuss this and this in the following slide. But some of the biocatalytic we have discussed as we gone through, we can go a bit faster. Are you following? Yeah, this one mainly we will look at enzymes, I would say, mainly enzymes. But I'll give you some examples. And some of the microorganisms, the names are very strange. Don't bother with them. Just to give you the feel. That today is just introduction. Okay, let's come to the. Okay, if you look at biocatalytic, I think there are 2 slides on this. If you look at S, what is S prime? S prime is a co-substrate. Co-substrate in our case, what is our co-substrate? It's our oxygen. What is our primary substrate of our interest? Glucose. So if you notice, I use this to discuss again and again. Are you following? Yeah, it's always glucose. Yeah. So we have got. So there are different ways. What is the one method? How do we measure glucose? So can you tell me how do we measure? Summarize for me. Farhan, I give you one chance first.
What?
I want to measure glucose. What are the methods we can use to measure glucose? We have gone through it. In fact, it's summarized.
pH.
What is that?
pH.
Good.
Drop of oxygen.
Yes.
Right, and hydrogen peroxide increase, right?
Yes. Okay. Actually, you are given a lot of answers. Okay, maybe I'll say it in a better way. We can monitor this reaction, the glucose detection, based on a few methods. First one, monitor the consumption of the co-substrate, that is oxygen, correct? We can measure oxygen because it is electrochemically active, correct? That's one method. What's the second method? Measure the change of pH, correct? Yes. What's the third method?
Hydrogen peroxide.
The formation of hydrogen peroxide. Is it correct?
Mm-hmm.
Yeah, so you can do it 3 ways. Basically, this is the whole, the gist. Okay, in this case, we are very lucky because glucose reaction has so many products. And the co-substrate, they have got different interesting properties, right? They are all electrochemically active. They are not change the pH. But this one I can't detect by optical because I don't think glucose acid and glucose has got change of optical density. Yeah. Let's say just as a hypothetical one, if this analyte is very strongly absorbing, are you following? Then what is going to happen during the catalytic? During the course of reaction, what will happen? The absorbance will drop if there's a catalytic reaction. Is it correct? Yeah, that is one way. But here we are looking at electrochemical and also what? Change of the pH. Yeah. Okay, go to the next one. We go to the next one. This is bioaffinity. Biocatalytic. The enzyme can be used many times. Okay, this is we are going to come and visit this. Okay, the natural, what is the original state of the enzyme? It should be in the oxidized state. What is the enzyme I'm referring to in this case? GOX. Are you following? The natural state of the GOX is what? Oxidized state, GOX. Are you following? Okay, during the catalytic conversion, when it's playing the role as a catalyst, what happened to the state of the enzyme? Really? If you see initially it's oxidized state, so after it had done the catalytic reaction, what happened to the enzyme? It becomes reduced. Are you all following? Yes?
Yes.
Yeah. Okay. In the previous case, case number 1, oxygen is a natural oxidant that brings back the enzyme back to the native state. What is the native state? Oxidized form. So oxygen is the natural oxidant for the enzyme. Are you following? It brings back to the native form. Then of course it can play the role again. Got it? Okay, but in this case, if you notice if you like, here I'm still looking at the glucose reaction. Gluconic acid is not formed. Even hydrogen peroxide is also not formed. Okay, in this case, we have an artificial oxidant for the enzyme. Are you following? Okay, the artificial mediator that carry out the role of the oxidation or conversion of the enzyme back to the native state is a mediator. Are you following? So we have another compound. What is the magic compound? What is that compound? The mediator, alright? So the very common mediator is actually ferrocene. Okay, ferrocene, when we go to the lab, you can smell it. It smells like, on the word ferrocene, what does it tell you? Yeah, got iron, alright? Yeah, got iron. So it's actually Fe2 plus 5 ring. Is this 5? Yeah. Are you going? Yeah. This is represented as Fe1, CP2R. Okay, some of this has got R, certain group, but for us, everything is I just put as a simple, just H. Okay, what is the role of this mediator? It what? It converts the reduced glucose oxidate back to what? Oxidized back to the native state. Are you following? So that means it becomes natural, it can play the role again. So in this case, the electrode is a bit special. We are actually trying to oxidize back the ferrocene back to the ferricene. So this is ferrocene. So this ion is actually ferricenium. This is ferrous, right? This ferrous ion. We can get Fe3 plus. I think the spelling is correct. Yeah, become 3 plus. Take note, this thing doesn't change. All these rings stays the same. So which is the active part that will change? Like you did, Dr. Teo, I'm sure has started the lecture. You got big enzyme. Not the whole part of the enzyme take part in the reaction, correct? It's only which part?
Active side.
The active site. The active site usually contains what? Metals, correct? Could be zinc, could be iron, what else? Those are the common ones,
Copper.
right? Huh? Copper, that's correct, yeah. Zinc, copper, iron. I can't name others. Of course, not lead, not cadmium, not
Magnesium.
Oh, magnesium, for that one is for what? In the chlorophyll, right? Yep, things like that. It's only that part. Take note, in this particular, we are going to revisit this slide. This is important. Usually I'll set something in the exam along those lines. Take note, in this case, we do not measure the oxygen. We do not measure the gluconic acid. We do not measure H2. Actually, we are measuring what? The final signal I'm going to measure is actually oxidation current of ferrocene to ferricinium ion. Are you following? So in fact, this one advantage, write down, one advantage of this type of glucose detection is good. The background oxygen level, because from sample to sample oxygen level might change. The baseline stays the same. This measurement is independent of the oxygen in the sample. One advantage. You can write this down. Yeah. Yeah, from sample to, because if you look at this reaction, is there any oxygen among the equation? There's none, yeah. So the variable oxidation level doesn't matter, will not affect. Actually, for measurement of the other one, the oxygen, that one will be crucial. Because when you do calibration, you only do one calibration. But if different sample already have different original oxygen level, so actually the drop might not be correct. Alright, so this is one possible way to measure the, glucose as well. So this measurement is independent of oxygen level in the sample. Alright, the next one, what is the next one? Biocomplexing, antigen, antibody, DNA, correct? Yeah, or bioaffinity, based on molecular assembly. And can you circle the word irreversible? Yep, irreversible. That's the key word. The major difference. Yeah, one bind. Antibody antigen is very strong. And because of such a strong binding between two of them, it is very sensitive usually. The detection is extremely sensitive, more so than the biocatalytic kind. Yeah. So for this kind, usually it's very useful for pregnancy tests, to know whether the hormone has changed. It's very sensitive in that sense. Okay. Take note. Which one is a more popular method, bioaffinity or biocatalytic? You think which one is more common? This is less actually. If you look at less, biocomplex biosensors have not reached the maturity of biocatalytic. So class A is lots of, even though the advantage is, very sensitive, can be extremely sensitive, but it's not so widely used. I'm sure there are no commercial bioaffinity biosensor being sold. Enzyme one, very common, very mature, yeah, but well characterized. Alright? This one. Okay. For us, I will come and visit the antibody antigen. DNA, of course, somebody has to do the assignment as well. Yeah? Alright. You can teach us. The antibody antigen, nobody is doing. I will do a little bit in the class. So usually, which one is the antibody antigen, which is the bigger one? Why is that? Antibody is how many times bigger? I don't know, is it like 1 million to 1 time? Yeah, I know. It's 1 million to 1 time, that's our ratio. Yeah. Alright, let's move on. Okay, ion channel, this one will come up, nothing will come out in that way. Ion channel, this is actually molecular as well. It's molecular as well. Biocomplexing. Not so important, just to get you the feel. Let's look at the electrode kind, more interesting. Okay, if you look at this one, okay, just how I mentioned benzene, correct? Phenol, is it correct? Phenol has got only one OH, but this one, catechol, has got how many OH? How many OH are there? 2, yeah. They are related like the brother-sister compound, group of compounds, yeah. So it's an oxidase, a polyphenol oxidase. So it's an oxidation, though the H get dropped out. So if you look at this reaction, so you're going to get ketone. You're going to get the ketone. So this is actually the measurement, if you notice, isn't that a bit funny? What is our interest actually? What is our analyte of our interest? What is the analyte? Catechol, is it correct? Catechol. Yeah, this is what we want to analyze. Yeah. But during the reaction, the enzymatic reaction, we get the ketones. Yeah. Get the ketone, and this ketone form, we get back this one. Yeah. But of course, the amount of catechol we are going to get might not be exactly like the original amount. So this one, we don't detect it directly. Probably the kinetics is slow. Probably this reaction is faster. Are you following? Yeah, no? Yes? Yeah. So probably this reaction is much faster. That's why people prefer to use an enzyme for the detection of the catechol. Are you following? Yeah. There could be all the possible brother-sister compound. The OH might change. That could be auto, beta, para. They are different. Maybe some of these we might have a CH3 group might change. So this is just a group. It brings back to Dr. Wong's earlier part to do separation. And of course, some of these are more toxic than another. Okay, if you look at, do you see this and this a bit similar? Why there's a group that's similar, right, with the OH group. Okay, what is dopamine? Any idea? Any idea? Yes, very good. Neurotransmitter. So take note, some of the phenolic compound, it can interact if we had too much of the pollutant, the food we consume. It may mimic the behavior of the dopamine. So it might become a bit crazy. Yeah, because it affects the nervous system. So that big interest. So, okay, this enzyme, what is PPO? Polyphenol oxidase. Okay, this, just now, when I mentioned GOX, it only acts on glucose. Is it correct? Take note, this PPO, it acts on a group of the related compound. It's not so selective. Do you see? Yeah, of course, we always say enzyme very selective just on one compound. Probably sometimes I have to broaden the definition. It acts on a class of related compound, like in this case. So PPO will catalyze this one as well. Catalyze this one, so what do we get? We get the O, double O there as well. Are you following? Okay, take note. These PPO, they are present in what items? Those few items. Yeah. Those things, can we eat those? We can eat olive, we can eat apple, cucumber, we can eat mushroom. Yeah, we can eat this our food. Yeah. So this one, maybe how do we extract the enzyme out? What is a good way? Grind it. Yeah, ideally we should grind it, yes. As fine as possible. You use a mortar to grind it. Alright? Yeah. So in this case, do we have to immobilize the enzyme? What do you think? I don't have my pure enzyme because it's in the natural matrix. So actually the natural matrix, the cellulose, whatever present inside. So when I use a tissue, usually we don't immobilize because the natural thing is like a protective coat for the enzyme present. Are you following? So this one actually no, I just mix everything like a rojak actually. It functions. Yeah. So this type of enzyme is very cheap actually. If you look at the next thing, so in this particular case, copper. Yeah. So this one literally no immobilization. In fact, it's just a physical mixing. No chemicals involved. I just put graphite. Graphite is just graphite powder, powdery. Powder, then how do, if I put powder and banana, what will happen? Would they gel? Would they gel? Not so good. I need a bit of oil, neutral, a bit of those silicone oil to gel them. Take note, graphite powder is too powdery. It flies everywhere. We always have to use some oil to put them together. Okay, so you think the graphite powder, this electrode is very easy to make. So graphite, yeah, powder, they are fine particles. Then I'll put a bit of oil, okay? So you think what type of oil? So in this particular new jar, I think it must be a type of silicone oil. Yeah, we cannot use cooking oil or whatever. So you have to use scientific oil. It has got certain formula. if I use too little oil, what will happen? Like if you have rojak, right? Do you put just 1 tablespoon of peanut sauce, or you put what? You have to put until enough, correct? If you put too little, they will not mix, it will not gel, and then the rojak will taste bad. So for the graphite powder plus the the oil, it had to be in the correct proportion. If too little, what will happen? Too much air holes between the particle, resistance will be very high. Correct? Too much air gaps. So I have to put until enough, until everything stuck together, correct? But if I put too much oil, what will happen? Too much of a good thing is always bad. What will happen again? Cairo, what will happen? Take note, this oil is non-conductive. Resistance also increase. If I don't put enough, a lot of air, just like I mentioned, it's a lot of air. Air is non-conductive. We want it to have good electrical conductivity. Can you see? Then I keep add a bit. There's an optimum ratio usually. There's a formula for it. You all gel, very nice. All graphite powder are in contact, good conductivity, correct? Okay, now I'm a bit greedy, measure a bit too much oil. Oil is non-conductive. Resistance increase again. You get back the same problem. You got it? Yeah. And of course, the plant tissues, we want what? This one you do optimization. You put a bit of banana, too little enzyme, right? Of course, response very low. If you put more, you increase. But eventually, too much of the banana inside, the response will also drop. What is the problem? Can you speculate?
Too much matrix.
No, non-conductive. Because banana is non-conductive matrix. Same thing. Initially, the response is low. What is the reason? Not enough of what? Enzyme too little. Yes, you increase fine. The response increase. You come to a plateau. When you add too much, response sure drop because it's non-conductive already. Yeah. So these are some things you have to watch out. This one, okay, this one just very fast. This is if you look, this is a piece of what I did with one of the students. So what is this one? Can you see the naming? Can you see the naming of the biosensor? What has come out? That's right. It's electrical. It's electrochemical. That's correct. Transducer comes out in the naming. What's the other one? What is that? Analyte is fine. In fact, the bioreceptor also comes out. Do you notice the bioreceptor also comes out? Turnip also comes out. Yeah. So this one you can see the way it is. Yeah. Actually, if I put hydrogen peroxide electrode, it's also okay actually, as a title. Are you following? Yeah. So this one was under tissue. All right. Let's go through very quickly. If you look, okay, the names are very scary. This is what? This one, if I say microorganism biosensor, so I name the biosensor based on what? Bioreceptor, not based on transducer. Are you following? Yeah. Yeah. So the microorganism is there. So you think where should the microorganism be? I suspect this one is I think it's it consumes oxygen. If you look at the many layers, yeah, I think it consumes oxygen. Must be. Yeah. Where should the bacteria has to be at the front here. Yeah. Okay. We can use. So this one, the structure can be quite complex. Let me look at. Okay. This one we won't go through. Can we just look at the? Let me see. Which one take the longest? Which Which analyte take the longest time?
Vitamin B.
What is that? Vitamin B1. Okay, vitamin B1. All right. Take how long? 366 hours. One day can't even do one experiment. Of course, you need to have multiple devices. Yeah. Okay, which one is a good one? Methane, very fast. Actually, sometimes doing 2 minutes when you are impatient is really long actually. It's true, it's true. Okay, this one just to get you the few microorganisms, they consume different items. Don't memorize the, for somebody who do environment, maybe this could be, you might want to talk about, I don't know how you want to approach it. Could be because some of these analytes are environmental item. Okay, what is meant by this range? Can you comment on what is meant by the range?
Detection.
What is that?
Limit of.
The linear range.
Uh-huh.
The range where the biosensor can detect the analyte. Okay, if you want to, which one is okay, shall we look at this one? Look at this one. Look at this one. E. coli, glutamic acid, E. coli. Okay, this one, I use the word, it has one order. You understand the concept of one order of magnitude? That means from 10 to the power 1, it detects to 10 to the power 2. Is it correct? Yeah? Okay, if you look at glucose for number 2, it's also one order of magnitude. Okay, which is a very good one? If you look at nicotinic acid, in terms of the range, it is extremely good. How many orders of magnitude are there?
6.
Is it 6?
6.
It's 6, right? About 6. Yeah, that one 5 is 10 to the power. Yeah, about 6. About that. So nicotinic acid detection for this particular sensor based on this bacteria is very, very good. Do you understand? Yeah. Ideal bulbs, you have a wide range. But take note, sometimes nature is like you cannot have everything good. And this one is special because it is also very sensitive. Sensitive 10 to the power -5. You don't see any of those in that range. Do you understand? Yeah. So this one just to let you, I just sensitize you, to let you feel that some they are good in terms of response time, some they are good in terms of what? The linear range. Are you following? This slide doesn't tell us the lifespan of the biosensors. Do you think it's a lifespan of the biosensor important? I don't every day immobilize my enzyme. Yeah, whether the enzymes are stable or not. So this slide can't tell, doesn't tell us the information. So this could be one factor you should consider if you are to develop a biosensor. Correct? So let's say now what are the factors you can tell me? The range. Range can be from 1 millimolar to 1,000. It also can be from 0.1 to 100. The order of magnitude is the same, you understand? But it's different sense. You understand what I'm saying? You can take from 1 to 10 to the power 3 millimolar, and the other one is actually from 0.1 to 10 to the power 2 as a linear range. The order of magnitude change is the same. Is it correct? Yeah, it's the same. Are you following? Okay, what are the factors we should consider if you want to develop a good biosensor? What is the first factor? Jason?
Cost.
What is that? Cost, yeah, okay. Ruben, next one.
Range.
Range of response, linear response. Hui Li, one more. Based on the, what is that? Sensitivity, sure. Cairo?
Response time.
Response time, yes. I don't have a sensor that after 1 day only can get one reading. Some are really like that, 6 hours. What is the other one, Farhan?
Lifespan.
Lifespan, yes, that's correct. And the lifespan, that means if let's say that electrode can last just 2 days, another one can last for 1 week. Yeah, sometimes you have to wait. But in nature, there's no such thing as a perfect one, you understand? Perfect one, that means all the companies have to back up. This one can make a magic electrode that's good for everything. What is the next one? Okay, these are some of this slide, I think we can skip this slide. Some of these you might use it for your assignment, is it okay? Yeah. Okay, let's look at this one very quickly. Take note, we are going to, usually antibody is represented as the Y, is it correct? As the Y. The antigen Ag is what? The small bit. The antigen could be what is that? Could be something from our body, could be a biomarker for a disease, could be something from the toxin from the environment, things like that. Alright? Usually antibody is a very small part. They interact. Let's say when antibody antigen interact, are we forming a bond? What do you think? Are we forming? It is not a true bond. You cannot say like covalent bond. It's not. Because we are not really forming it's not like that. It's just they interact, certain component interact well. Yeah, usually we use the term affinity constant. K affinity is very big, could be things like, I don't know, 10 to the power 10 or something like that. That means very strong. In fact, if it's so strong, the backward arrow technically should be what? Very
Small.
very small. The forward, you can make of course when we draw, forward very long, backward very short. Alright? Okay, just maybe last example, we just go through. I think this one. Yeah, okay. Let's go through. Okay, this one is actually for heart attack. For heart attack, yeah. Myocardial infarction. So this one, there's a particular marker, troponin T. You see, before a person get heart attack, the level, you see the red item really peak, is it correct? Yeah. Okay, what is the method used in the hospital? Hospital, they measure, I think, the CK, one of the enzyme. I think this one is in the liver or whatever. One of the enzyme, or in blood, I guess. Take note, if you look at the levels, it's very low. But then hospital, what do you think? Do you think hospital prefer to use which one? Hospitals, they will not use this method. They will not use this. They still want to use the old tradition. To change the protocol in the hospital is like moving Mount Everest, alright? Even though we researchers will prove that actually that one is a very good marker to predict whether somebody is going to have you understand? But sometimes to change the hospital process is like moving Mount Everest, almost. So no doctor will ever want to touch unless I don't know how people will lobby, you understand? Yeah. So this is one of. Okay, the next one is actually, the next one, why is this one? This is actually to test for Hui-Li. Maybe Hui-Li, I'm sure I've gone through this test, HCG, for pregnancy test. It's normally the based kind of sensing. Okay, this one, this one maybe I'll just explain a little bit. This is actually an enzyme. The enzyme is catalase. The enzyme, this is actually the antibody for that particular compound is already immobilized. So this antibody, what is it? It's a bioreceptor already immobilized on the surface. Alright. If I am already pregnant, very advanced, quite advanced, like 2 months pregnant, I'll have lots of this, you understand? I'll have lots of this, lots of the diamonds. So, and this, they are fighting to go to the surface. Is it correct? Are you correct? They are fighting to go to the surface. Then the one that's stacked with enzyme will have very little one. What will happen? If there are lots of these, lots of the diamonds, that means the pregnancy antigen. So what will happen to the one with the E? Does he have a chance to go up there? No chance, very little, very little. I'm just talking about relative, very little. So the one with the enzyme, so actually this probe, after we do the incubation, this probe will be used, I will put it in the what? Catalase solution, H2O2 solution. You have to detect, you have to form these products. Are you following? Yeah. So if I'm very pregnant, the signal I'm going to get here will be very what? Low or high? That means the very little enzyme actually. That means it will not catalyze the decomposition of H2O2. Are you following? Because there are lots of these pregnancy advanced, lots of these already present. So this detection is a little bit, if the rest is as this one go up, that one will go up, you understand? This is actually the one. Is it reverse? Because I got, if you are pregnant, lots of this will be there. Are you all following me? Or do you want to say the case somebody who is not pregnant? Somebody who is not pregnant, nothing of this. That means lots of those tagged enzyme all will go up. That means this surface have lots of enzyme here. Is it correct? Lots of enzyme, what will happen? That means the composition of the H2O2 will be very one. The catalysis will be very fast because lots of enzyme. So this one, we always have to use the same amount of H2O2, is it correct? Yeah? That probe, what is this probe? This one, the detection is a bit more tedious. This whole probe has to be transferred into a solution containing what? H2O2 of a fixed concentration. Fixed concentration. Are you following? Yeah, it's a little bit more tricky than the normal way, like those. Yeah, there's a bit of competition for the. So this particular antibody, we call it the enzyme label antigen. Yeah. Are you following? Yeah, it's labeled. Okay, one more thing, I'll just make sure. So the amount of labeled antigen has to be the same. I always introduce, every sample I introduce 5. Yeah, I introduce 5. And this one, is it always 5? This one depends on how pregnant or not pregnant. If somebody who is not pregnant, what will happen? The 5 will just happily come here, is it correct? Yeah? If this one, there are hundreds of these, very pregnant already, what will happen? This one got no chance to come. Is it correct? Yes, if I ask you to explain during the exam, did you can? The concepts. Have fun.
Can.
If somebody is very pregnant, we have lots of which one? Lots of this one, right? 100 with 1, who will come up here first?
The 100.
The diagram will all come. Any enzyme on the surface eventually? No. Then it will not catalyze H2O2 decomposition. You look at the extremes of. What are the 2 conditions that we fix? What are the 2 solutions that we have to fix?
H2O2 and the amount of label.
That's right. The amount of the labeled antigen has to be fixed. Yeah. Correct. But is it okay?
Antigen or enzyme?
No. The labeled one is with enzyme. The label is actually catalyst. The E is the catalyst.
So if you say control the amount of enzyme is also
Yes. Literally the amount of control, the label antigen is controlled because that label is labeled with enzyme.
Yeah.
That's right. Actually, indirectly, it's actually.
Get it.
Yeah, that's correct. Yeah. Let me see. We will end here. Let me see. Yeah, we will end. Let me see. Okay, class, can you read up a bit of the characteristics of an ideal enzyme? I think I might. Hello. The characteristics, precision of this, you read up on your own. I will just explain. Go and read up what is meant by hysteresis. Maybe that term you might not have heard it. The rest I think is quite standard. I think we can. Yeah, hysteresis. Read. See the rest. Maybe you can go a bit faster. Yeah. Okay. We can go on. Yeah, I still see you next. Next week I don't see you, right?
Alright.
So you enjoy your high, yeah. The rest enjoy your break.